So let's take a look at reference frames. This is something that Newton had long figured out. So to put it in context, let's imagine that you're in a physics lab and you're trying to measure the gravitational potential energy of an object. Right? So you have a ramp, there's a ball bearing that's going to slide down that ramp, comes up perpendicular, you map the trajectory, figure out how far it's gone, calculate the kinetic energy, that was the potential energy. Now in doing so, you are looking at the potential energy from the top of the ramp to the bottom of the ramp or the top of the table. This disregards the fact that you have a height that goes down to the floor. If you were to drill a hole in the floor, there could be a basement or some other store you could go to. So when you're looking at your potential energy, mass times gravity times height, where you measure that height from is relative. Similarly, when you're measuring the speed of that ball bearing, you're measuring it relative to the room you're in. And you don't have to worry about the fact that the Earth is spinning on its axis, despite what some other people on YouTube say, or that it's revolving around the sun. We can ignore all of these effects and measure relative to the lab, because that lab is our reference frame. So that's what reference frames are all about. And Newton came up with the transformations, how you convert from one reference frame to another. Because sometimes you are in motion. So if there's a park bench and you're sitting on it reading a newspaper, car drives by on the street behind you. So here's our basic car. That car turns on its headlights, and that light comes out at a certain speed. The way Newton would measure things, it would be relative to you. So if you're on the park bench, you might say this light has gone 3 meters because it was emitted over here and it was detected over there. That's a 3-meter difference. But if you're in the car and you're measuring relative to itself, you might say it's gone less than 3 meters because your car has driven and covered some of that space. You might say it's only gone 1 meter. We're going to assume this is an impossibly fast car. That is the difference of reference frames. So in Newton's day, 2 different observers would measure 2 different positions, so we're going to call that x and x primed. They would agree on how much time had elapsed, so they would disagree on the speed. So knowing this, in Newton's day they were saying, well, in some very specific cases, you would have a preferred reference frame. Things would be a little bit wrong. So if you ignore the fact that the Earth is moving, your predictions are going to be a little bit wrong. That Coriolis effect. It's often called the Coriolis force. It's not really a force. It happens because angular momentum is conserved. If you're on the surface of the Earth and you jump, the Earth moves under you while you're moving. And while you do have some momentum, as you jump, you don't cover the same amount of distance as the Earth. You might have seen that in figure skaters. Figure skaters who have their arms out spin more slowly than figure skaters who've pulled their arms in. That's because the angular momentum is conserved. As you get further away, you slow down. So if you jump straight up and you move high enough and your equipment is precise enough, when you land, if the Earth is moving in this direction, you'll actually land a little bit to this side of your initial reference point, because your conservation of angular momentum means you don't spin as fast as the Earth. So in Newton's days, this seemed to cause a problem. But Newton was the one who said, well, no, sure, there's a preferred reference frame. And if we look out at all these stars, we can do our math, we could figure out what that preferred reference frame is. And then if we find the star in the heavens that moves at exactly that speed, well, then we just haven't found the preferred reference frame. We found the heaven in the heavens. So the Christian theological heaven. And that was enough in Newton's day to resolve it in the minds of most scientists. There was a preferred reference frame out there that had a special meaning in the universe. And we could eventually find it, and that would tell us something about the world we live in. So that is the first piece here. The next piece we need to talk about with the origins of relativity is electricity and magnetism. And that's the topic of the next part of our Day 1 video.